Thanks to Brilliant for sponsoring today's video.
There's a fairly large overlap between people that enjoy math and people that enjoy chess. So it stands to reason that someone has combined the two. And in fact, there's a rich history of mathematical problems in the setting of a chessboard with chess movements. And we're going to look at one such problem today. And well, we're going to look at a special case of it. We're going to explore Knight's tours on 3 by N chessboards. So let's look at a quick definition. A closed Knight's tour is a path that a knight takes on a chessboard that visits every square exactly one time, and it starts and ends at the same place. So I guess you could say that it visits the starting point and the ending point twice, but I think we kind of have an idea of what a Knight's tour is based off of this definition. Now, I'd like to point out that there's also something called an open tour, which has a different starting point than it has as an ending point. But like I said here, we're going to only look at closed tours. And our goal is to determine when a closed Knight tour is possible for these special 3 by N chessboards. So can we classify the values of N where such a tour is possible? And in fact, we'll come out with a full answer at the end of this. Okay, so as a little bit of experimentation, let's look at what's going on with the 3 by 4 and then the 3 by 5 chessboard. Okay, so let's start with this 3 by 4 chessboard. So I'd like to point out that this vertex right here, the bottom left vertex, you can only, or the knight I should say, can only move to two other vertices. And that's this one up here. Notice it's one move right and two moves up. Or this one right here, which is two moves right and one move up. But since it can only go to those two vertices, that means that any tour has to, in fact, go from one of these vertices to our magenta one to the other one. Because I think you'll notice that any such tour will pass right through a vertex. In other words, there'll be an edge going towards the vertex and an edge coming away from the vertex. Okay, so anyway, out of that, we get that this has to be part of the tour. This edge right here and this edge right here. And I guess it goes without saying that what we're doing here is shrinking the squares on a chessboard down to these vertices in a graph, and then we're adding edges to mean the movement of the knight. Okay, so now let's do the same sort of argument on this vertex up here. Okay, so this vertex up here, the top left, is attached to this one here, and let's see, to this one here. And by our same argument, it has to take a path maybe from one of these and then to the other. So in other words, it has to be connected to both of those vertices. Okay, so that already gives us some sort of restriction of what the Knight's tour might look like. Okay, so now let's go ahead and go over here to this middle-most right vertex and play the same sort of game. So notice that this middle-most right vertex, that's connected to this one right here and this one right here, and only those two. So let's see, that means we have to have these two connections. But actually we can see a problem because we've just created maybe like a sub-cycle inside of, well, what would be this Knight's tour. In other words, if you start at this vertex, you can, for instance, never get to this vertex over here because all of our moves have been forced. And likewise, you can play the same sort of game starting with this upper right, this lower right, and then this middle left, and build, well, another sub-cycle, which those are two disjoint tours, but not one single thing that's all together. Okay, so anyway, we can see here, based off of the argument that we've just made, that it's impossible to have a Knight's Tour on a 3x4 chessboard.
Hey there, I'd like to take a minute to talk about today's sponsor, Brilliant.org. I've been talking about Brilliant for a long time now, and that's because I truly believe they are a great example how to have fun with learning. Brilliant is where you learn by doing, with thousands of interactive lessons in math, data analysis, programming, and AI. Each lesson comes with hands-on problems so that you can truly learn the material. In fact, it's been proven to help you learn 6 times more effectively than just watching videos. The content is designed by an award winning team from MIT, Caltech, Duke, Microsoft, Google, and more. Brilliant is also something you can take with you on the go. The mobile app makes it easy to pick the time that works for you. Check out their course library. They have a new range of comprehensive courses in math that's built for learners of any level. Whether you want to brush up on your fundamentals or challenge yourself with advanced concepts, you'll find yourself enhancing your visual and spatial problem solving skills. But we're scientists here, so don't take my word for it. You should test it for yourself. Treat yourself to a unique hands-on experience by going to brilliant.org/Michael Penn for a 30-day free trial and 20% off your annual subscription. Thanks once again to Brilliant for sponsoring today's video.
Now, let's see about a 3x5. So maybe we'll play the same sort of game. Let's start up here, and then we'll likewise do that for this vertex in the bottom left, and that's going to go here and here. And now let's go over to the right-hand side, and instead of using that middle vertex, let's use the maybe 2 corner vertices. Using the same argument, this one on the corner has got to be connected to this one right here, and, well, it has to be connected to this one right here. Oh, but there we have a problem because, well, it's forced to be connected to this one right here, but that forces 3 edges entering that one vertex. And if you play the same game over here with this lower right, you'll observe that it's attached to this one right here as well as this one right in the middle. And so I think you can see that any sort of Knight's Tour that we would make, well, not really a Knight's Tour, but Knight's path that we would make would go through this vertex twice. Once maybe from blue to yellow, and then once from magenta to orange, or really any combinations of those 2 colors based off of the path. Okay, so check it out. It's impossible in 3x4, it's impossible in 3x5. And now let's see if we can check 3x6. So we just played a game with 3x4 and 3x5 chessboards, and now let's look at what's going on with 3x6 and then 3 by some odd number chessboards. We can actually do these all at once, which is a pretty nice result. Okay, so let's look at 3x6 chessboards. So we're going to play the same kind of game that we did before. So now let's observe that this upper left vertex must have a path going to its 2 possible neighbors here, just based off of our previous argument. So that means it has to have edges going to those 2 vertices. And then this lower left one likewise has to have edges going to these 2 vertices. And then next up, let's notice that this middle one has to have edges going to these 2 vertices. Again, using that same argument over and over and over. And now, well, we can repeat this over here on the right. So let's see, this upper right is connected to these 2. And then let's see, this lower right is going to be connected to these 2. And then finally, this middle right is connected to these 2 right here. Okay, cool. But now what I'd like to do is zoom in on what's going on with perhaps this pink vertex, which is stuck in the middle, or this pink vertex over here, which is also stuck in the middle. And, well, let's observe that each vertex has to have 2 edges emanating from it. I think that's, like I said before, pretty clear from our definition over here. So that means, well, we have to have 2 edges emanating from this vertex. But let's see, what is this vertex connected to? Well, in fact, it's only connected to 2 possible vertices. this one up here like that, or this one down here like that. Those are the only two vertices that you can get to from the pink colored vertex in one move. And then similarly over here, this one can only achieve this and this. Now, if you don't look at that very closely, you might say, oh, well, we've got a Knight's Tour. But if you just glance at it a little bit more closely, you'll notice that there is nowhere for this vertex to be connected to otherwise. Or in other words, when the knight gets here, there's nowhere to go. And that's actually going to be true not only for this vertex, but the one over here, and then its companion 2 on the top as well. So, well, that means that it is impossible to have a Knight's Tour on a 3x6 chessboard. And now let's look at this case of a 3x2n+1, so a 3x odd chessboard. So here we're going to use a little bit different of an argument. So what I'll do is I'll color each of the vertices in some sort of alternating manner. So I'm going to use magenta and blue. And so it's going to be alternating just like a chessboard might look like. So we've got something like this over here on the left. But then observe that since we've got an odd number of columns, this is going to start and end, or each row is going to start and end with the same color. So that tells us that we're going to have a magenta right here, a magenta right here, and a magenta right here. And then likewise, we can fill in the blues. The blues are all of the others. Okay, cool. So we've got something like this. And then the next really important thing here is to notice that any knight's move will start on one color and end on another color. So let's say our knight starts on this blue one right here. Well, then the knight is allowed to move over here to this magenta one, or down here to this magenta one. Or if the knight starts right here on this magenta one, well, it can only move either up here to this blue one or over here to this blue one. In other words, the knight always moves from one color to the other. Or blue to magenta, or magenta to blue if you want to like be specific about the colors. Okay, but then let's also notice this second fact, and that is that any tour passes through the same number of blues as magentas. But then if it passes through the same number of blues as it does magentas, that means that there are an even number of squares on the board or vertices in the graph. But then also, we can count up the number of vertices by this formula right here. So what that tells us is that 3 times 2n plus 1 is even. In other words, 6n plus 3 is even. But that's a pretty clear contradiction because that's an odd number. So what did we contradict? Well, we contradicted this implicit assumption right here that in fact we had a Knight's Tour on a 3x odd chessboard. Okay, so maybe I'll leave it as a homework exercise to check the case when you have a 3x8 chessboard, and you'll see that it's impossible to have a tour there. And let's jump to the next place where it is possible, or I should say the first place where it is possible, and that's a 3x10 chessboard. Okay, so now let's look at the first or the smallest 3x10 chessboard that exhibits one of these Knight's Tours, and this is a 3x10 chessboard. So how we're going to start this is start at the right-hand side and the left-hand side and put the forced moves in there. And these are the forced moves that we've seen before, like for instance, this one right here, and this one right here. And then likewise, this one right here, this one right here, and this and this. Again, those are ones that we worked with way back on the 3x4 chessboard even. Now let's go over here and do the same ones. Well, really kind of a mirror image of those same ones. Okay, cool. So now we've got those. And now the plan is to work off of those to create maybe the rest of this thing. Okay, so let's see how this might go. So let's maybe start here and see where we can link. So let's maybe take a long down and rightward path like this. So 2 moves in that direction. And then we're gonna go over to this one in the middle that seems like it's kind of easy to miss. And then from there, we're gonna bounce up to this one and then make a sharp downturn. Then we'll make a sharp upturn again, go back right a little bit, and then finally link up with this one over here. Okay, cool. Now, well, what are we gonna do next? So the next stage will be built from this vertex over here. So let's observe that at the moment it can only move one place, and that is over here, kind of this rightward trajectory. And then we'll make another rightward move up here. And then from there we'll go back sharply down and then back sharply up to hit this one that's in the middle that again seems like it would be easy to miss. Then we're forced to go down and right like this, and then up and right like this. And then finally we'll make this down and right move to this position. Okay, so now we've only actually got 2 more moves to make, and those will complete the Knight's Tour. And that's gonna be to connect these 2 vertices, and then maybe symmetrically these 2 vertices over here. And now, well, you can see that we've completed our Knight's Tour. And then I guess I should say that there is a 3x12 case as well. So we've got a 3x10 case and a 3x12 case. And now what we'll end up proving is maybe the big result of today, which is that for any even number, there's always a 3x(n) Knight's Tour. And for any even number, there's always a 3 by that even number Knight's Tour. So let's see how that goes. Okay, so the idea for this claim, which is for all n bigger than or equal to 5, there's always a closed Knight's Tour, is to use induction, where the induction hypotheses are the 3x10 board and the 3x12 board. So we exhibited the 3x10, I'll let you look up the 3x12. And now here's the idea. We take our larger board and we break it into 2 pieces. So one piece that's a 3x4 board, and then another piece which is everything else. And we know that there's a Knight's Tour on, well, the rest of those over there. And they always end in this shape that I've exhibited. And then, well, here's the big trick, is we're going to erase this edge. So we remove this edge from the old tour, and then we use the fact that now those vertices can be connected to 2 new things. Oh, and I should point out that here we have that connection, so we're leaving that one. Okay, so we're erasing that edge, and then we're gonna make the following 2 connections between the old part and the new part. Okay, so there's our connection from old to new. And then after that, the game is to find a new Knight's path. Really, it's an open tour through this 3x5 board that has this as a starting point and this as an ending point. Okay, so let's exhibit one of those. So we can go in this direction up here, then make a sharp down, and then after that, go back here, and then up here, and then back down here. So let's observe that a lot of these moves are the ones that would be forced on the left-hand edge anyway. So we in fact don't really have to think about those. And then this one is next gonna go up here. That's kind of the only thing that it can do. And then back here, again, kind of the only thing that it can do over here. And then let's see, now the end is in sight. We can go up here, over here, and then connect with what we had before. So let's see, we've got an old tour over here, which we know is a closed Knight's Tour. And then, like I said before, we remove this edge. Observe that this edge is on this new left-hand side, so that's always going to be on the left-hand side. We remove that edge, add these 2 blue edges, and then create a new open tour starting at this vertex and ending at this vertex. And then we've kind of glued these two things together, if you will. Meaning that if we, for instance, started over here with a 3x2 K-tor, then over here in the whole thing, we have a 3x2K plus 4 tor. But then, since we've got two induction hypotheses, the 3x10 and the 3x12, that means we can leapfrog our way up to this main result. And that's a good place to stop.